Hi everyone. Today we begin section A in our syllabus, Principles of Chemistry. This is topic 1, States of Matter. So our objectives for today are to state the evidence in support of the particulate nature of matter, explain the differences between the three states of matter in terms of arrangement of particles, explain the changes between the three states of matter in terms of energy and arrangement of particles. So let's look at the states of matter. First of all, matter is anything which has a mass and occupies space. So all matter is made up of tiny particles that are in constant motion because of the kinetic energy they contain. This is a theory called the particulate theory of matter, also known as the kinetic theory of matter. So for every theory, you must have evidence to support it. So to support the particulate theory of matter, we have terms such as diffusion, osmosis, and Brownian motion. So, Brownian motion. The concept of Brownian motion was named after a man named Robert Brown. So in 1827, he used a high-powered microscope and observed constant irregular motion of pollen grains floating on water. So take a look at this. This is basically what he saw. This big green dot represented the pollen grain and the blue circles represent water. So water is constantly in motion, and because of that, it allowed an irregular movement of the pollen grains to show up. So there was no external factors actually affecting the water. This is a natural movement of water. Now we have diffusion. Diffusion is the spontaneous movement of particles of a substance from a region of higher concentration to a region of lower concentration, and it happens in all states of matter. So say for example, we have a bottle of perfume, right? So if we open our bottle of perfume, the particles inside here will begin to move from an area of high concentration to an area of lower concentration. So outside, where there's no perfume particles, this is an area of lower concentration. So this will continue happening until there is an even distribution of the perfume particles. Now diffusion can also take place in liquids. For liquids, diffusion can be shown by placing a drop of ink or a crystal of purple potassium manganate into a beaker of water. So here we have a drop of purple potassium manganate. It's basically like a solid purple dye, and after some time you're going to notice that it moves from an area of high concentration to an area of lower concentration, and this is going to keep happening. It's going to keep spreading until a uniform purple color is found. Now I want you to think about something. In which experiment will diffusion take place at a faster rate? Would it be this experiment with liquids, or would it be this experiment with gases? So take a quick minute and pause this video to figure out which one will happen at a faster rate. So let's see if you were correct. The speed of diffusion is fastest in gases, followed by liquids, and very slowly in solids. This is because gases have particles that have a higher kinetic energy. All the particles move very fast, so to distribute other particles within it will take place at a faster rate. Now in liquids, those particles have a little less kinetic energy, therefore things would be moving around a little bit slower. The rate of diffusion increases with temperature. So looking at the previous experiment again, if we were to repeat it using one beaker of hot water and one beaker of cold water, this is what you will notice. At higher temperatures, the particles have higher kinetic energy and hence move faster and diffuse at a faster rate. So again, just like gases, because it's hot, there's more energy between its particles and things would move around faster in here. As compared to a beaker of cold water, those particles have a lot less energy and anything between it will move around a lot slower. Now, another factor to consider is that the rate of diffusion depends on the relative molecular mass of the particles. This basically means that heavier particles will diffuse at a slower rate than lighter particles. So this is one experiment that we usually do. Alright, so here we have a glass tube that is corked on each side with a rubber bung, and there's cotton wool soaked in ammonia on this side, and this side has cotton wool soaked in hydrochloric acid. Right? So gases will be emitted from these cotton wools, and then somewhere they will meet in the middle. So when they meet, they react to form a ring of ammonium chloride. However, it's actually closer to one end of the tube than the other. Which gas particles move faster? Well, the ammonia particles have traveled further down the tube, so they must have diffused at a faster speed. So looking at the relative molecular mass here, if you look at your periodic table, this is nitrogen and 3 hydrogen atoms. Alright, so this forms the ammonia molecule. If you look at the mass of the nitrogen, it's 14, and the mass of a hydrogen atom is 1. Right, so we have 3 hydrogen atoms here, which means when we add up the masses, we get a relative mass of 17. If we calculate the mass for HCl, H is 1. Don't forget to look at your periodic table. And chlorine is 35.5. So when you add the masses together, you get a relative molecular mass of 36.5. So this is the heavier molecule, and this is the lighter molecule. So lighter molecules will diffuse faster, right? And this is where it will form. Now, a chemical equation representing what is happening here: ammonia in its gaseous state plus hydrochloric acid in its gaseous state will give you ammonium chloride in its solid state. These are some molecules that you will have to remember over the course of CSEC chemistry. So osmosis is another phenomenon that provides evidence to support the kinetic theory of matter or the particulate theory of matter. So what is osmosis? Osmosis is the movement of water molecules from a region of higher water concentration to a region of lower water concentration through a partially permeable membrane. It is a special type of diffusion carried out by plants to obtain water and mineral salts from the soil. So let's say, for example, this is our semi-permeable membrane. Semi-permeable means that only some things can pass through it. Say, for example, we have a root. A root can have a membrane such as this, and inside the root will represent this side, and outside the root will represent this side. So if there's more water outside the root than inside of the root, the water molecules will go through the semi-permeable membrane from an area of high concentration, like this, to an area of low concentration until it is evenly distributed, right? So this must take place using water molecules and a semi-permeable membrane. If it does not include these two things, it's not osmosis. Let's look at some other practical applications of osmosis. So one way would be controlling garden pests. The skin of a snail or slug is a semi-permeable membrane. So if you put concentrated salt solution or just throwing salt on the pest, it will cause water from inside of the animal to be drawn out of the skin. And that movement of water from high concentration to an area of low concentration, which is outside, it will cause the animal to die from dehydration because they will end up losing so much water. Have you all ever tried throwing salt on a frog? Another application is food preservation. So, bacteria and fungi are most common causes of food spoilage. Both these cells are enclosed by a membrane. So this is the semi-permeable membrane. If a food is placed in a sugary or salty solution, then any bacteria or fungi present will lose the water in their cells to the more concentrated solution outside. When this happens, the cells will shrivel and die, and the food will not become contaminated with loads of bacteria and fungi, right? So this is one way that we preserve food. We can preserve it either using a very high salt concentration or a very high sugar concentration. So that would be, for example, jams or jellies, or for salt, it will be like salt fish and so on. Let us now look at the states of matter and their properties in a little more detail. So our properties are arrangement of particles, compressibility, attractive forces between particles, kinetic energy, and particle motion. So for solids, the particles are very close together in a very orderly or regular fashion. The forces of attraction between the particles are so strong so that movement is very limited to just vibrating about a fixed point. This is also very hard to compress. In a liquid, the particles are further apart. The arrangement is less orderly. Forces of attraction are weaker, so the particles are able to slip slowly over each other. And this is what gives it the liquid type of movement. There is only slight compressibility in liquids, but there needs to be a lot of pressure in order for this to happen. In gases, particles are very far apart and are haphazardly arranged. The forces of attraction between particles are so small that the particles are able to move freely in all directions at high speeds. Now, gases are easily compressed. State in which a substance exists depends mainly on its temperature and pressure. For example, iron is a solid at room temperature and pressure, but at around 1500 degrees Celsius, it becomes a liquid. Similarly, oxygen is a gas at room temperature and pressure, but at minus 183 degrees Celsius, it's a liquid. So here, what I want you to do is download this PowerPoint file and click on this link, and it will carry you to a little quiz so that you can be a little more familiar on state changes. So let's first look at melting. Melting is the change from a solid to a liquid, and we know this already. When ice melts, it turns into water. The temperature at which a solid melts is called its melting point. A pure substance has a fixed melting point, right? So when a solid melts, it turns into a liquid. These particles will have to gain energy in order to become a liquid. For freezing now, freezing is the change from a liquid to a solid. It is the reverse of melting. The temperature at which this occurs is called the freezing point. For most pure substances, the freezing point is the same as the melting point. So here, liquids must lose energy to become a solid. Boiling is the change from a liquid to gas or vapor. So if we continuously add kinetic energy or heat up a liquid, eventually the molecules or the particles will gain so much energy that it will overcome the forces of attraction that it has for each other, and then it begins to vaporize or it begins to move randomly, right? So The point at which it loses its forces of attraction to each other is where it becomes a gas. So at this point, it's called the boiling point. For example, the boiling point of water is 100 degrees Celsius. Now, boiling is a little bit different from evaporation. So evaporation is the change from liquid to gas without boiling. So there is no need to boil something in order for it to evaporate. Think of your clothes drying on the line. So another example is a drop of ethanol or perfume evaporates at room temperature. It also occurs below its boiling point, only at the surface of the liquid, slowly, and it has a cooling effect because of the heat energy absorbed from the surroundings. Condensation is a change from a gas to a liquid, so it's the reverse of boiling. In condensation, heat energy is released and the gas particles slow down and move closer to each other to become a liquid. So from gas to liquid is condensation, and from liquid to gas is evaporation. Sublimation. Sublimation is a change from a solid directly into a gas without melting. For example, iodine crystals here, this is a solid iodine, they sublime into purple iodine vapor when heated. So when the solid is heated, these particles have very weak forces of attraction. So just a little bit of heat will cause it to sublime. The opposite of sublimation is called deposition. So that's where when you cool down a gas, it will directly turn into a solid. Other examples include dry ice, ammonium chloride, and naphthalene. So just to summarize what we did today, we have three main states: solid, liquid, and gas. So as we add energy to the system, it's absorbed and it melts. Then we continue adding energy, it boils and evaporates until it becomes a gas. And in the other direction, when it cools, energy is released and it condenses into a liquid. We further cool it down, energy is released again, and it freezes into a solid. And from solid to gas is called sublimation. Gas to solid is called deposition. So that's it for the lesson today. This is a quick check with some questions that you have to do. So again, pause the video and attempt these questions in your notebook, and the answers will be posted on Edmodo Wall. Right? So please look out for part 2 of my next video, heating and cooling curves. This is where we will be discussing different types of graphs. All right, so that's it for today. Bye.